Right, hello everybody. This is a supplemental video to my series on heteroskedasticity and Univariate regression. This video shows you how to derive the formula that I showed in my first video in the case of one variable, one constant, OLS regression. Enjoy.
Alright, so we'll start with a normal linear model, which with yi is equal to alpha plus beta xi plus threshold error term epsilon I. It's just a normal linear regression model with one variable and a constant. Right. Now, we know that our estimator is given by beta hat equal to the sample covariance between xi and yi divided by the sample variance of xi. Right? So when we plug in the yi here, what do we get? We get, well, the alpha kind of cancels out. Then we've got beta covariance hat of xi with xi, which is just the sample variance of xi, divided by the sample variance of xi, so this cancels out, plus the sample covariance of xi and epsilon I divided by the sample variance of xi. All right. Now we're going to do a few tricks. So first of all, we'll move the beta over to the left-hand side. So we've got beta hat minus beta is equal to the, and we write this out, 1 over n sum. I'll leave the I equals 1 to n out here just to make it a bit simpler to look at, otherwise it looks quite clustered. The sum of xi minus x bar epsilon I minus epsilon bar divided by 1 over n sum of xi minus x bar squared, or if you want we can also put a n minus 1, the degrees of freedom adjustment, also in the upper one. But for now, because it just makes it a bit easier if we work without the degrees of freedom correction, I'll leave them out. Okay. And now we do another trick. We multiply with square root n, which means here we've got 1 over square root n in the numerator. Okay, now what will we do? Now we apply the law of large numbers so that each of the sample means converges to the population equivalent. So x bar converges to the expectation of x, and epsilon bar converges to the expectation of epsilon. So this means we've got 1 over square root n sum of xi minus mu x times epsilon I. Remember that the expectation of epsilon is 0 by assumption, or actually by construction, because we include a constant in our population regression equation here, the alpha. So we would divide this by 1 over n sum xi minus mu x. Don't forget the square. All right. So that's the first time we apply the law of large numbers. The second one, we can also apply it to the denominator. This converges to the variance of xi. This is just an expression for the variance, straight and simple. All right. What do we do with the numerator, the thing we've got up here? Here, we can actually apply the central limit theorem, believe it or not. So what's the expectation of that thing we've got up there? The expectation of xi minus mu x times epsilon I. There are two ways to go about this. You can either use orthogonality, or you can use mean independence assumption. Usually we use mean independence assumption, so I'll do that here too. So we use the law of iterated expectations. So then we've got the expectation of xi minus mu x. The xi only depends on xi, and the mu x is a constant. So when we've got the conditional expectation, conditional on xi, we can simply move them out. Now by this is 0, by conditional independence assumption, which means this whole thing becomes 0. Great. We've got the mean of our normal distribution when we apply the central limit theorem. Now, what's the variance of this? The variance of xi minus mu x epsilon I is actually very simple, because we've actually just shown that the expression in here is mean 0. So the variance of this is just the expectation of its square, the squared expectation of this. So this is expectation of xi minus mu x squared epsilon I squared. And that's all there is to it. Okay, so now we've got that 1 over square root n sum of xi minus mu x epsilon I converges in distribution to a normal distribution with mean 0 and variance of expectation of xi minus mu x squared epsilon I squared. Okay. So now when we go back, we also divide it by the variance of xi. So what we now have is that the distribution of beta hat minus beta, with a little abuse of notation, is a normal distribution with mean 0 and variance expectation of xi minus mu x squared epsilon I squared, and then close the brackets, divided by the variance of xi. Now, when we want to get the overall distribution, we want to pull the variance of xi into the normal distribution. And because the normal distribution is mean 0, we multiply the whole thing with a constant. And with the standard rules, we get that we've got square root n, beta hat minus beta converges in distribution to a normal distribution with mean 0 times or divided by the variance of xi, but 0 times a constant is 0, so it doesn't affect the mean, but it does affect the spread, and we have to square it when we pull it into our variance here. 0 expectation of xi minus mu x squared, epsilon I squared, divided by the variance of xi squared. Okay, fantastic. Close brackets. Here we've got our expression, and this is the general form for the variance. Now, just out of curiosity, how do we get here to the standard variance under the homoscedastic case? So in that case, we've got that square root n beta hat minus beta converges in distribution to a normal with mean 0, and sigma squared divided by variance of xi, that's under homoscedasticity. How do we go from here to here? Well, it's quite straightforward. The assumption that we use is that the expected value of epsilon I squared given xi is equal to the unconditional expectation of epsilon I squared. So knowing x doesn't tell us anything about the variance of epsilon, so to say. And that we denote with sigma squared. So now, when we look at the numerator, we've got the expectation of xi minus mu x squared, epsilon I squared. Use, again, the law of iterated expectations. That's one of the most useful things you will ever encounter in econometrics. Make plenty use of it and practice it. So this becomes the expected value of xi minus mu x squared times the expected value of epsilon I squared given xi, and take the expectation of that. Right. This is a constant. This is sigma squared. So now we end up with sigma squared times the expectation of xi minus mu x squared. But this is just the variance of xi. And then when you look at the expression here, this one, now you can see that the numerator and the denominator cancels one of the variance of xi. So now we've got that the expected value of xi minus mu x squared epsilon I squared divided by the variance of xi squared is equal to sigma squared variance of xi divided by variance of xi squared. And then this is just sigma squared divided by the variance of xi. Now, because we want to feel fancy, we put this empty square to show that we've finished our derivation. There you go. So now we've looked at what's the actual general version of the variance. It's given again because it's so nice. Let's paint it with red. That's this expression as I alluded to. And we've shown how to go from here to the version under homoscedasticity. Now, because we've shown this, let's get away with a question mark Put an exclamation mark because we've shown how to get there. But again, to get there, we needed this assumption. Oops. We needed this assumption. This is the no heteroskedasticity assumption. We also, actually we didn't speak about this because we're in a cross-sectional case, and we made use of the assumption as well that there's no autocorrelation in the errors. We did this at another point. Just bear this in mind. Autocorrelation, the error term, is typically covered in time series analysis and in panel data analysis. So I'll leave these topics for the future. This is the cross-sectional, simple cross-sectional case. Thank you.
All right. I hope you enjoyed this supplemental video and it made things clearer. Maybe you can leave me a comment or send me a message if you like this format of videos where I actually show you how to derive it myself and not just show the steps to get there. That would be very welcome feedback. And don't forget to like and subscribe to see the rest of the series on heteroskedasticity and the other videos and course links that I posted. Thank you for watching.